This is the question I asked in the first part of this video lecture, and if you're doing it through Moodle, then you already know the answer. So, all of the rules we know for informal flux still have to apply for our formal flux definition. And so note, in particular, that all of the field lines that enter the back surface also go on to exit the front. Well, and so all of the lines go in and out. That means the total flux must be 0. Note, as well, there's no charge enclosed in the surface. And we know that the flux out of the surface has to be proportional to the amount of charge inside. And that's true whether we're working with the formal definition or the informal definition. That argument that the total flux through this surface is 0 is the key argument we need to figure out our angle dependence. So note that this means that the flux through the back, which is negative, plus that positive flux through the front is 0, or in other words, the flux through the front is just the absolute value of the flux through the back. And the point of this shape was that the back surface is perpendicular to the E field, and so calculating the flux through the back is straightforward. It really is just the magnitude of the E field times the area of the back, where I've been able to drop the absolute values because the E field strength is a magnitude of a vector, and so it's positive by definition, and an area is always positive, and so I don't need those absolute values anymore. The rest is all geometry, and maybe you already see the geometry. In particular, there's a little bit of trig, but in case you don't see it, I'm going to go through it slowly and carefully. So first, let me define some lengths. The back surface is just a rectangle and has some width w and some what I'll call length L back. And similarly, the front surface has exactly the same width w, but some other length that I'll call L front. Now what I really want is the flux through the front in terms of the E field and the area of the front with whatever angle dependence. And so I want to replace this A back with something in terms of A front. Well, notice A back is WL back. It's just a rectangle. And so all we need now is a relationship between L back and L front. Well, we can get that from this triangle. I'm going to pop that triangle out. This side is L back. This side is L front. This angle theta here is the same as the angle in the top corner of the triangle. And so L back is just L front cos theta. Well, that's everything we need, because I can now plug that in here and get that the flux through the front is now all in terms of things to do with the front, the E field through it, the width of the front, the length of the front, and the cosine of the angle that the front surface makes with the perpendicular. And notice that WL front is just A front. And so here is my expression for the flux through the front surface. And that is now, aside from dealing with sign convention, my more complete formal flux definition, where note that this angle theta is defined as the angle that the surface makes relative to being perpendicular to the field. So on my to-do list, I had angle dependence and sign convention, and we've got the angle dependence now. Before I deal with the sign convention, I'm just going to write down a more compact way of writing what we've got already. And to do it, I'm going to define something a little odd. I'm going to define an area vector. And the definition of it is that it's a vector that points out of a face on the surface. It has a magnitude which is defined as being equal to the area of the face that it's pointing out of, and its direction is perpendicular to the face and outward, right? It doesn't point in to the surface, it points outward. So with that definition, now look at how that area vector at the front is related to the E field vector. Notice that the angle between them is the same as this angle theta that's between A front and the perpendicular to the E field. But wait a second, we've seen this before. When we have two vectors and we want a quantity that is the magnitude of the one vector times the magnitude of the other times the cos of the angle between them, that's what we call the scalar product, or also we call it the dot product. And so this is a nice compact way of writing it because that includes the cosine theta inside it. Let's look at how that plays out at the back surface. Remember that the area vector points outward, and so this A back vector is pointing back this way, and the E field vector is the same at the back surface as it is at the front surface. Well, now notice that the angle between A back and E is 180 degrees. Wait a second, cosine of 180 degrees is -1. And so this is giving us the negative flux that we want here. And in fact, anytime the E field is coming into a surface, the angle between the E field and the area vector will be greater than 90 degrees, and we'll get a negative flux. So not only is this a more compact way of writing our flux, it also deals with the sign convention, and so this is our fully formal flux definition. Well, fully formal except that it only applies if we're talking about a uniform field through a flat surface. Most of the time, unfortunately, we're not calculating fluxes through flat surfaces. Most of the time we're dealing with the things like cylinders and spheres and such. And so we definitely need to know how to deal with non-flat surfaces and variable fields. So here I've drawn a curved surface and a non-uniform E field through it, and I'm indicating that this is the outside and this is the inside. So this surface must curve around and meet itself somewhere down here. And let's now think about how we deal with the flux through this. Well, the way we deal with it is a familiar way. We can talk about splitting the surface up into little chunks. And now each chunk has some area, let's call it delta A, and so I can define for each chunk an area vector which is perpendicular to that chunk, which I'm approximating as a flat plane, and so we would call that area vector delta A. And there is some angle between that area vector and that E field. And so now I can say this is the ith chunk, so I'll call this delta AI, and the E field through it is what I'll call E sub I. And so I can now simply say that the total flux through this surface is going to be approximately, because these are not really flat faces, a sum over all of the chunks, E dot delta A. Well, I think this is probably looking pretty familiar to you, because all we have to do now is take a limit as our sizes of our chunks go to 0, and we get an infinite number of pieces that we're splitting the surface into, and our flux is going to be now not approximately, but in fact equal to an integral over the surface, which may have you a little worried, but we'll see that it's not so bad. E dot, and these delta A's turn into dA vector. And so that is the way we will do it, except that there's a special notation that if the surface is closed, then we just indicate that in the notation with a special symbol. We take the integral sign and we put a little circle on it, and that just means that this is an integral over a closed surface. That probably looks scary, but as you'll see as I work some examples of it in this lecture and next lecture, it's actually not so bad. Fundamentally, all we're now doing, going from our informal statement of Gauss's law to our formal statement, is defining units. In our informal way of calculating things, we had a flux, which in this case would just be one line out and two lines in. Note that these charges aren't of equal magnitude, and so that gives me a -1, and that is equal to the enclosed charge times the lines per unit enclosed charge. So what we've got here is the idea that the flux is in some way proportional to the enclosed charge. And so that's what we want in our formal statement. We want that our flux, calculated by the new formal way we have of calculating it, is equal to some constant, a proportionality constant that we have to determine, times the enclosed charge. And so that's our goal. So since now we know all we're looking for is a constant of proportionality that we need to solve for, I'm just going to find the flux due to the simplest thing we know, which is a point charge. Now, a point charge, as I've already discussed in an earlier lecture, has spherical symmetry. We can rotate it around any line through it, and it doesn't change it. We can reflect it through any plane that includes it in it, and it doesn't change it. That's spherical symmetry. And so the field due to it has spherical symmetry, but that just tells us what we already know, which is that the field is radially out from it, and that at any distance r away from the charge, the E field has the same magnitude everywhere at that distance. And importantly, the E field is perpendicular to a spherical surface that I draw around the charge. So we match the shape of our surface that we're working with for the flux to the symmetry of the object. The object and the field have spherical symmetry, so we define a sphere of some radius r, and we're going to find the flux through that sphere. Well, so we know that that flux is going to be E dot dA, integrated over the whole sphere. But note, because it's a right angle, and E dot dA is E dA cos theta, remember that theta is defined as the angle between the E field vector and the dA vector, and the dA vector points perpendicular to the surface and outward. And so theta is 0 and cos of 0 is 1, and so we don't have to worry about that angle. And so that's simplified our flux. It's got rid of all the vector symbols. It takes care of the dot product. We just get EdA. E is the same magnitude everywhere on this sphere. And so this E here is a constant. And so since it's a constant, I can pull it out of the integral. And this integral is now just summing up all the little area elements on the sphere, which means all it is the area of the sphere. And now we're pretty much done, because we know what the field is due to a point charge. That field is kq over r squared. And this area is just the area of a sphere, so it's 4 pi r squared. Notice the r squareds cancel out, so in fact I would get the same flux no matter what radius sphere I defined. Think about that in terms of the E field lines. It makes sense. And so there we have it. Our flux is 4 pi k q. And q is the enclosed charge. All we were looking for was that the flux had to be some constant times the enclosed charge. And so this 4 pi k is the constant we were looking for. Often we define a different constant epsilon naught, which we'll talk about more as we go on in the course, which is 1 over 4 pi k, and part of the reason to define it is that it makes Gauss's law a little more compact. It becomes the enclosed charge over epsilon naught is equal to the flux through the closed surface.